Okay, so since we all are here researchers, this presentation is also going to be another small experiment. So I tell you beforehand that this is not like as, well, the format of this presentation is not going to be like the usual that, well, that you are used to. So it's going to be a small experiment. So anyway, so today's talk is going to be about the transfer of reinforcement learning for a robotic skill. So, well, my name is Adriana. And in this presentation, we will talk about the motivation. So in this presentation, we'll talk about the motivation that led this work, about the problem that we wanted to solve. We're gonna briefly discuss we're gonna talk about the solution, but briefly discuss the system implementation. But we're gonna focus more about how we evaluated it and what research questions we were interested in, and of course about the analysis. So, well, the motivation of this lies into the three important fields that this work reaches, which is robotics. As we all know, well, robotics keeps being a disrupting technology that, you are very familiar with it. Now it is very used in the industrial applications, but it started for further applications such as exoskeletons, social care systems, and well, much more other applications. The second is reinforcement learning that, well, in these latest years has been amazingly progressing. So beginning in the 90s, where the first AI agent was proposed and beat the human ability to play a game, until 2 years ago, where the 18 times world champion player was defeated by Aalto. And lastly, we're going to use transfer learning, which is also a very huge field, but in our specific applications, we are interested in how it helps, how it's going to help us to take the learning from a simulation to a real-world application. So, tasks that are difficult to program explicitly can be stated as a Markov Decision Process. And stating tasks in this way, well, let us use reinforcement learning, as we all know. So, just to briefly recall what an MVP is, an environment can be shaped by a probability distribution, and the agent or the robot is driven by a policy. A policy is fed by the states and the reward that the environment is able to provide, and the policy then dictates the actions. So according to how we shape this policy, is how we say that there's going to be a learning. So if the policy gets changed, well, then we say that there's some learning in there. So the problem that we want to solve is related to one specific problem, reinforcement learning challenge when using it in the real robots, which is the physical wear out that can happen when several iterations of the reinforcement learning happen in the robot. So one of them, well, obviously is the physical wear out. The second one is that the robot's response might also vary over the time, with this high number of repetitions. And well, this is just the one challenge, and other challenges are the state space dimensions, and some other. I want to make this group. So due to this, there is a trend to use transfer learning for reinforcement learning using a simulation, and then transfer that learning to a hardware. So one work, however, the previous work that we checked have used some kind of prior knowledge for the reinforcement learning algorithm. So, for instance, in this example, some simulated data was retrieved from a simple simulator, and then perform the reinforcement learning in the real hardware. And similar proposals have been done in the same hardware that we used for this work. Like for instance, in these cases where the programming by demonstration was used. So as we see, there is an introduction of previous knowledge. So to make this difference to these works, we were interested in using a model that learns from tabula rasa state. So, another way of saying that no previous knowledge is in use. So then we say, okay, we have the algorithm. Now let's talk about what robotic task we want to use. And we selected the basketball as the robotic skill to use, mainly because of three reasons. The first, because, well, as we see, the hardware can be moved in a way that resembles the way that a real player would do. Secondly, because the cost function is intuitive. The cost function was shaped as the distance from the ball to the target, which is the basket here. So the further the ball is from the target, the higher the cost, and the closest, well, the least cost that we get. And again, the third reason was because the way we stated this robotic skill as the Markov Decision Process. We stated it as using the ball as the state and as the action as the joint angular velocities. So our work involves the transfer from a simulated environment to a real-world environment. And in transfer learning, these are called source task and target task. So the reinforcement learning will happen in the source task from a simulated environment, and we will only transfer the learning obtained here. Okay, so our reinforcement learning stage involves two main things. So as we said, we're not getting into many details due to time constraints. But we can say that the first major player was the reinforcement learning algorithm, which was PILCO. PILCO, well, again, the most important things about PILCO is that it is a model-based algorithm, that it learns from tabula rasa, and it learns, well, one of the major stages is that it creates a dynamic model, Gaussian process dynamic model of the environment. In this case, the dynamic model was to learn the dynamics of the ball. And then once learning this dynamic model, then it performs a policy search by a gradient search. And well, it is an iterative process, as you can see. The second major component is the environment where we would use PILCO. So the environment was LWR4, which was a project being developed at the same time almost at the same time than this thesis was being done, and it consists of the simulation of the Kuka robotic arm in the environment of Mujoko. Mujoko is a physics engine. And well, as we stated before, the states are going to be the ball position and velocity, or well, the ball tracking, and the actions are the joint and angular velocities. Now, our transfer learning stage involves three players. To have the same interaction with the environment that we had in the LWR4, to keep track of the ball, we developed a vision system through a camera that kept track of the position of the ball. The second player was the implementation or the execution of those angular velocities in the real robotic arm. And the third player was the introduction of a policy adjustment proposed last year which involved the usage of the policy learned in the source task, and then through an adjuster, it would modify the actions in a way that the behavior observed in the source task is executed in the target task. So the dynamics, the ball dynamics that we saw in the source task would be repeated in the target task. That's the aim of this policy adjuster. So the complete process was divided in 3 phases. The first one is reinforcement learning of the skill in the source system with PILCO. So we have PILCO and we have LWR4. So through these, through the usage of these 2 players, we have a policy learning. Now, this policy, the policy learned, is executed on the target system first through a non-adjusted policy. This means to use the policy just exactly as how it was learned in the source system, and then through the policy adjuster, modify the policy parameters in a way that the behavior observed in the source system is replicated in the target system. And well, it was in the paper for which of this adjuster, it was proposed to perform iterations with an increasing data set. So when we shaped the experiments, we had interest in the research questions, mainly about 2 things: about PILCO generalities, meaning how it works, what were the implications, how good it would learn when moving from a scenario that is not that complex to a more complex scenario, and how good it would learn the model depending on the training data size. And on the other side, we also were interested into, since PILCO learns from tabula rasa, meaning learn from nothing, how does it increasingly learn precisely to perform the basketball skill? And about the transfer learning, the experiments were designed with thinking, or we were interested in knowing what were the implications of executing the policy in the source task, from the source task into the target task. And we also wanted to know the comparison between the non-adjusted policy and the adjusted policies. And because the policy adjuster was based on 2 supervised learning algorithms, we wanted to know what's the generalization error that these models had. So to begin with, we started with preliminary experiments, which helped us to solve the previous questions, and we found out that there's a big jump when moving from a simple scenario to a more complex scenario under the same settings. So, we call the simple scenario of the MATLAB simulation, and the same task in this preliminary experiment let us see that we needed almost like 5 times the same number of iterations to learn almost the same policy. Now across this axis, we played a little with the training data size to know, if we provide half the training data size, how many iterations you need to learn the same thing. And we saw that when the training data size was divided by the half, we almost needed like twice, or maybe here more than twice, the same number of iterations to learn the same thing. So now, when we executed PILCO on the LWR4, we found out some interesting cases to understand how it progressively learned. So due to the first position, well, to the home position in which every execution started, we realized that most of the times it started throwing the ball, well, because of the position the movement could be upwards or downwards, and if you move well, to the downside, obviously you have a worse result from the beginning. I mean, it would like annihilate completely the rest of the experiment. Whether if you start moving to the front, you have better chances to but you have better chances to learn something from that same policy. So another interesting thing was that sometimes it proposed or it learned how to move so slowly, in such a way that the ball would roll like around, well, over its body and like in this direction. Another one that actually emphasizes a lot why it's good to learn from scratch in a simulator is because it can do very dummy things like this. In this way, it was learning to move the ball like in this direction to decrease the cost. I mean, to get the ball closer to the basket. But as you can see, well, this was not a very wise decision because, well, it would retract on itself and it would crash. And well, this was actually in my opinion, one of the most interesting because it learned how to throw the ball to the air, like in making like an elliptic throw, like in a way that a regular basketball player would do. However, this policy was not practically possible because first the velocities, the high velocities observed in the upper joints generate a high torque alarm in the lower joint, and LWR sim does not count with an alarm for high torque. It just counts with a limit for the maximum velocity, but not for torque. So in the end, we proposed, okay, you're gonna learn with low velocities, and it learned to move in such a way that obviously it would move slowly, but and it would approach the ball like in this direction, and then it would let go. So we're gonna see a small video of it. So about the transfer learning experiment that we conducted, we selected the two policies to compare with. Both of them were observed the behavior described by the low velocity figure that we saw, meaning that we had like 50 degrees maximum for the joint angular velocity. And it required, well, in both of them, a similar number of optimizations. And as you can see, in the low bell one, we learned with half the training data size. And in the second one, we learned with the full training data. Well, this was actually very interesting because it almost required the same number of optimizations for different training data size. So now, to conclude this analysis about the transferability, this is important to recall. It is said that the transferability of a state is of high value when the experience displayed in the source task agrees to the experience displayed in the target task, and is of low value when these experiences do not match. So, to recall this, we compared the experiences, well, in this case, the ball position states observed in the source task, which is this red one. Of course, because this was tracked in the simulator, is very nicely followed with a simulation. And the rest of the trajectories correspond to the target task. First, to the non-adjusted policy, and then using the adjusted policies across every iteration. So, talking about the transferability, this is the target test, and this is the source test. So as we can see, there is a low transferability value. So linked to that, we can see here the actions from the policy for joint 2, joint 4, and joint 6. Since we have here low transferability, low value of the transferability, this can also be seen here, that the source task dictates an action that follows this pattern, and this pattern. However, the target task says, okay, according to what I saw, meaning according to the ball that I saw, I'm going to follow these actions. So although they start similarly, they don't obey to the same behavior. So with this, we can say that there is also a low value transferability on the actions. However, the position for each joint is, better followed according to the source task. So at least in the joint's position, the transferability showed a better value. So now let's compare just one result, hoping we're still on time. And that's the policy learned in LWR sim as the source task. This is low velocity, and this is how it was executed in a non-adjusted way. So it's low velocity, remember? Okay, so it's tried to go to the bucket, but not fully. And then this is when the policy is being adjusted, and this is the first iteration of the adjustment. Well, now it goes inside the bucket, but it shows a slightly different ball dynamics. As you saw, in the first one, there was a very low bounce. In the second, it bounced more. And in this, it bounced even more. And in this, it does as well. So, with this, we can draw the major conclusions, and we're looking at. We can say that for the implications of this project, let us say that it is reliable, but it is hard to say if these results would be valid for any other implementation of a system. So for our system, they stay reliable at least. However, it is very linked to the way that we developed the system. And this was interesting because as we saw in the video, we didn't require actually a lot of, just one adjustment of the policy was required to achieve the similar ball dynamics. And we need to say also that because of this low transferability value, the models, the policy adjuster didn't increase its added value to the following iterations because the error increased. Because the policy adjuster keeps increasing its training data size, and because we didn't have like a very reliable vision system, as we saw, it's hard to say if these conclusions would serve to any other similar system. So in the end, I want us to use what Brown Skills, what a researcher from the Stanford University said, in which they were also performing an experiment using transferability from a simulation to a real world learning implementation, and they also found that when moving from a less complex scenario to a more complex scenario, there was like a boundary where the performance got worse, and maybe this was surprising to them, and this is also surprising to us when we compare these results. So in summary, transfer learning for reinforcement learning is a suitable alternative to overcome the reinforcement learning challenge when using it in the real robots, if we mind how the MDP is stated, what algorithm is going to be used for RL and for TL, and of course, if we mind the implementation to ensure high value of the transferability.
Questions?
So what do you mean by optimization? You say optimization, you use the word optimization. I guess it can implicate many things, like how many steps you take in gradient descent, but do you mean how many iterations you do for the reinforcement learning algorithm? You do one trial and you update your policy to another one?
Yeah,
that's
exactly. Yeah.
One optimization is one trial?
Yeah, exactly.
Okay.
Yeah, that's sorry, maybe that was maybe not. Well, I failed into saying that when one loop of the PILCO algorithm is performed, yeah, we call to one loop one optimization.
Okay. Yeah.
Yes.
I have a question about the. So you said that your reward function was based on the distance of the ball from the target.
Yes.
Where was the target?
At the center at the rim of the basket, at the center.
Okay. So given that there is only one direction in which the ball would mostly entering the target, so from above or from mostly above, let's say, would you say that there is have you noticed anything like it would do something like pass very close to there but not really entering the basket or reaching that?
Yeah, actually, because it was the difference in the 3 dimensions, XYZ. There were some times in which it would fall here, and it would take it as a good learning. Sometimes preferred over when it was here, and there was no specific reason why select this side or this side. Yeah.
Could you see including also the direction of velocity or something like direction of motion in the reward functions in the model, as something that could help the ball getting inside, or was not a problem at all?
Well, we did when we were shaping the cost function, we kind of discussed it, but we decided, okay, maybe we should set as the target velocity as 0 because, we should ignore the target velocity because, yeah, it's hard to say, okay, when you reach this point, you should have this velocity. So we just ignore
or direction of motion, just.
Yeah, we didn't.
Okay.
So one more comment maybe about this is that the end condition of the episode, or basically when the reward, it was counted not until the end. I mean, it bouncing off. I mean, maybe you can mention that because that's all.
I forgot to mention that. So also the cost function was bounded by the moment of the first bouncing. So meaning that if the ball, let's say, would fall here, at that time the cost function would be trained, let's say. So
And also that if it hit the bucket, then if it bounced off, that was still, because that was the end of the episode.
mhm.
So then there was not anymore where it bounced, it wasn't
And
counted.
also, like when it bounces, it doesn't bounce in the goal position because there is no surface there.
Yeah,
Even in the
bounces.
success case.
Yes.
So it will always have higher, like it couldn't reach that position and stay there.
Yes.
Okay.
Yeah.
Yeah, there was a new paper like last year, Hindsight Experience Replay. I don't know if you have taken a look at it, but it's really like if you throw the ball and it bounces somewhere close to the bucket, you actually shape the policy like you look. But well, if I move the bucket there, it would actually go in. So it moves like the final. It showed.
But the thing is that I guess you were just trying for one fixed position.
Yeah.
Because you have to train it for multiple positions.
Yeah.
The way that they
Yeah.
studied, they said that we make the problem more complicated, but then we try train it easier. So
Yeah.
that's
So you learn more.
Yeah, there's no
Exactly.
no
So
such
you
thing as
learn the more
large.
general skill there,
Yeah.
even though, I mean, you.
Yeah.
I have, the way that I understood your work is that you have one policy, and let's say the policy is parameterized as it is the case for the PILCO. So the idea is that you want to start some initial random policy parameter in the space, and then in simulator, try to push it as close as possible, then to the final parameter, and then do a number of more shots on the real system to get actual learned model. So that's basically the way that I interpret your work. Yeah. So somehow you just want to find a good starting position for your optimization on the real system, and then do the final thing on the real system.
Not exactly, because the transfer, so like the learning happens here. So as you said, yeah, it starts from an initial position and then it performs the policy search, and yeah, so there is a point in which we select, okay, this is the policy that we want to follow. And that is the final, the final learning stage. And then the transfer learning, what does with this policy adjustment is to modify the policy and the source in such a way that the ball in the target task behaves the same as it behaved in the source task. So there is no further policy optimization, let's say, no improvement.
You don't do any further training on the adjustment.
Yeah, I do it, but for the inverse dynamics of the ball. So what I care about now is not reaching my target. What I care about is to make the ball in the target.
Correct dynamics instead of correcting the policy.
Yes.
But how do you correct the dynamics then?
Because you can observe the dynamics of the real system, which are not exactly what was simulated.
That's true, but then how do you adjust the action? So I guess the adjustment should be done by correcting policy parameters.
Because PILCO does it, it's a model base.
Yes, true.
So when you change the dynamics model, then of course the optimal action change.
Yeah, it updates the model first, and then using the updated model, it tries to
Yeah.
So then in that case, what I can say, if you just think in the parameter space, the goal is first to go as close as possible to some good initial position, then do the final, optimization on the real system. This can be sometimes interpretation. And in that sense, it is very close to the concept of meta learning. So basically what you can do, in this case I guess you have only one ball with one weight. And for the case of meta learning, you can consider different things, different tasks at the same time, and then trying to find a set of parameters which is close to all possible different combinations in simulator. And then now you can run it on the real system. this is something that I can actually link to this work. So this is some, how to say, connection to this concept. Another thing that I was actually, this is down to the question. Because you're learning the dynamics of the system on simulator. So PILCO actually learns the Gaussian processes for the dynamics you observe in simulator.
Yeah.
And then you observe the dynamic on a real system. And these dynamics are different from the simulator. But Gaussian process does not understand this. It just keeps adding data to that model. So it just grows the size of the model.
No. But that's yeah. Okay.
It's a different thing. So yeah, the Gaussian process. I'm sorry. The model learned by PILCO, like it stays there, and then the model learned on the simulation, like doesn't do anything further. It just stays there, and the the source task just provides the policy. That's all what it does. And then in the real system, we just get the policy that tells me, okay, you're gonna move you're gonna move in this way with this state. And as you said, the ball dynamics in the target task is different, and this is what the policy adjustment does.
So you learn the model again from scratch in the real system, using the policy.
Not completely from scratch, because it creates, based on the first execution, it creates a predictive model, which is the inverse dynamics of the ball. This is what is doing. What this supervised learning algorithm does. So it executes the policy, and it says, wait, where is it? Here. So it executes the policy as such in the target system, and it says, okay, if I ask you to do this and you move the ball in this way, now I'm gonna learn. I am gonna save this data, the training data size, and then I'm gonna create a model that lets me predict that in the source task I expected you behaved like this, and now you behave like this. So based on these two informations, then I can create a predictive model, which is what is called the inverse dynamics ball. And now with this mixture of this prediction, then it creates the adjustment on the policy on the target task that lets me have the same ball behavior that I had in the source in the target.
Okay, thanks.
Okay. I don't see any more questions, so thanks again, and thanks for all the presentations.